All right, so all of you know that the cryptography is a lot of mathematics, right? And so some of that math will be in the today's lecture, right? There is not a lot of math in this course as such, because we are a course on network security, but for cryptography part, we need some math part, right? So that math is today. So today we will talk about how to do GCD, okay, greatest common denominator or greatest common divisor, okay, so the same thing. And then we talk about modular arithmetic, and most of you should know mod 2 arithmetic, how to add things mod 2. Then we get into things which are called groups, rings, and fields, and Galois fields. You know, that basically about those and how to do polynomial arithmetic. So first of all, GCD, greatest common divisor. He said greatest common denominator. I think that would probably work as well. But to find GCD, you have to find out, for example, what is the biggest number, greatest number that will divide both 10 and 25. In this case, that number is 5. In this example, right? How do you find 5? Well, you could factorize both of them and then find out what is the common factors and then multiply them, but that's actually much more difficult than the method here, which is that you divide 25 by 10. Whatever remainder comes out, you divide that by, basically you keep, so you divide 10 by 25, you got 5. You divide 5 into 10 basically, and then you get 2, and then you got 0. Once you get a 0, then the last divisor is the greatest common divisor. So this is straightforward. The principle is not very difficult. All you have to do is take a number, bigger number, divide by the smaller number, whatever remainder comes out, divide into the previous divisor, and you keep doing this. This is not necessary that you will finish in two rounds. You might need, many rounds. The important thing is, whenever you get the 0 as a remainder, then the previous divisor is the greatest common divisor. This is called the Euclid's algorithm. However, there is a tabular method of doing the same thing, and so this tabular method requires 4 columns. They are labeled Q for quotient, R for remainder, U and V are the coefficient. And then we want to find out the greatest common divisor of 10 and 25. Now this you may not have done before, so please listen carefully. Even if you have done GCD by division before, you may not have done the tabular method, right? So listen carefully. And the first 2 lines are filled in by yourself. So the first line you write the bigger number, which in this case is 25, and then you write down 0, 1, and 0 here. What this means is, whatever is in the remainder column, if you multiply that to U and V, you should get equal to, if you multiply UI, this number with this coefficient, and 10 with this coefficient, then you should get RI. Every single row that will be true. But for the first row, this is true. If I take 25, multiply by 1, take 10, multiply by 0, add the 2, how much I get? 25. The second row, we write down the similar thing, 0 and 10, the second lower number, and then we write down 1, 0 here rather than 0, 1 here. So 1, 0. So now this thing that we talked about is true, because you take 25, multiply by 0, 10 multiplied by 1, you add them together, you get a 10. Right? Once you have written those 2 rows, the third row, the way you write the third row is that first you divide this last row, which in this case is right now second row, into the previous row. So 10 you divide into 25. When 25 is divided by 10, you get a quotient of 2 and a remainder of 5. Now, so these 2 things you would do. Now, once you take 2, then you do the same thing basically in other columns like you did in this column. You multiply 2 to this number, 2 times 1, and subtract from the previous number. That's what actually you did for the remainder here. What you did was you take 2 times 20 and you subtracted from 25 to get a 5. Right? Similarly, you do on this column. 2 times 1, subtract from 0, you get a minus 2. 2 times 0 is 0, subtracted from 1 is 1. Now, that property still holds. If you take 1 times 25 minus 2 times 10, you get a 5. Right? Ri is always equal to ui times xi plus vi times yi. If this is x and y. Ui times x plus actually. Ri is always equal to ui times x plus vi times y. So this is correct calculation, right? Now what we do is we take this last value 5, divide into 10 and get the quotient, which is 0. That's why this quotient is 2. Right? Now we do the same thing. We multiply 5 by 2, subtract from 10, we get a 0. We multiply 2 with minus 2, how much we get? Minus 4, subtract from 1, we get plus 5. Right? We take 2, multiply by 1, this plus 2, subtract from 0, we get a minus 2. Alright? The good news is that the remainder is 0. Once the remainder is 0, your process is done. At that point, the previous number is the GCD, 5, is the greatest common divisor. In addition, the advantage of doing this tabular method is now that we can write down equations like this, where 0 equal to 5 times x plus minus 2 times y. Right? However, if this last number was not 0, suppose it was 1 by some chance, and we will see an example where it is 1. If this is 1, last number is 1, then you can write down that uix plus viy equal to 1. And by the way, that means that the GCD is 1, which means that they are relatively prime. Relatively prime means the greatest common divisor is 1, means there is no number that divides both of them. So that is one thing, but also you know that this is equal to 1. So what this means is that if you were working on mod y arithmetic, then ui would be the inverse of x, because only when you multiply a number with its inverse you get a 1. Right? In the mod y arithmetic, this is all 0 anyway, because any multiple of y is 0. Right? When you have mod 5 arithmetics, 5 is 0, 10 is 0, 20, 15 is 0. So, right? The numbers are only from 0 through 4. So basically that allows you to get an inverse by this method. And there are many places in the course where we will need the inverse. So the only way to get inverse is to do this Euclid's algorithm in a tabular form. Alright? And here is the procedure. Exactly the steps that we did, I wrote it down here. Then I would like you to fill in this table right now. What is the GCD? 1. The greatest common. They are relatively prime. Right? So we can write down, okay, so the question is what is the last row that you have? And I need to write down the last row. So what did you get for the last row? Anybody? Go ahead. 0.
No, 7, 0, negative 15.
7, 0 even. 7, 0?
Yes, 7, 0, negative 15, 8.
Negative what?
Negative 15, 8.
15, and then plus, yeah?
8.
8. Before that, what was the row?
1, 1, 2, negative 1.
Okay, so this row is important, because what this is saying is that 2 times 8 minus 1 times 15 equal to 1. Right? 2 times 8 minus 15. 16 minus 15 is 1, which is correct, right? But it is also saying that if you were to do in mod 15 arithmetic, then 2 is equal to 8 raised to minus 1. Inverse of 8 is 2. Alright? So if you were to find out 1 upon 8, 1 upon 8 is equal to 2, because whatever the inverse of 8 is, when you multiply that with 8, you get a 1. So this number is important. This 2 is important to know. So now the homework. Find the multiplicative inverse of 5678 mod 8765. So everybody can do that, right? Basically, these are the two numbers. You write down the table and do the same table that you did a minute ago. Right? And if you don't get a 1, then there is no multiplicative inverse. Then that's the problem. But if you hopefully will get a 1, they might be relatively prime, and you will get the inverse. And the answer is 2527. Alright, now let's talk about modular arithmetic a little bit more. Modular arithmetic works almost like the regular arithmetic, except that all the numbers are less than the module, basically the base, or whatever you want to call it. So this is the arithmetic mod m. If you want to do x times y mod m, you can do x mod m times y mod m, and then whole thing mod m. Right? When you want to do addition mod m, you could do x mod m, where x could be much larger than a number than m, and then y could be much larger than m. First you reduce them to less than m, then you add them, and if there is more than m, then you again do mod m. Right? If they're less than m, then that's fine. Similarly, you can do x minus y. You can do powers x raised to 4. If you want to do x raised to 4, you can do x raised to 2 and x raised to 2. And both of them then do mod first, and then you do mod on the product. If you want to do x raised to I times j, you can do x raised to I and then raise the whole thing to j. So here's some examples. 125 mod 187 is what? 125, because it is less than 187, right? But what about 225 plus 285 mod 187? We do it in pieces. First, we reduce 225 to mod 87, and then we reduce 285 to mod 87. So this gives you 38, this gives you 98. Then we add, which is 136, which is less than 187, so that's all set. You're all set. We want to do 125 square. We do the square, we find out it's 15,625. We reduce it by 187, we get it 104. Right? We want to do 125 raised to 4. Now, you really don't want to do this first. Basically, what you do is you want to do the square first and then you square it later. So first you do the square and you get 104. Then you square the 104. Okay? Then you get 10,000 and you do mod now and you get 157. So that is 1 raised to 10 raised to 4. If you want to get a 6, you could do 4 and 2. And so 4 is 157, 6 is 104, and so the total is easy to calculate, and you get 59. Does everybody feel comfortable with the division, multiplication, powers and all that in mod? Okay. Alright, if you do, so let's just see. Set of all integers is z. So when we have minus infinity to plus infinity, every integer including 0, that we call z. When we say z sub n, we mean set of all non-negative integers less than n, which means 0 through n minus 1. So z sub 2 is 0, 1. G sub 8 is 0, 1, 2, 3, 4, 5, 6, 7. Alright? And now you can do all the arithmetic, subtraction, multiplication, addition, division, and all the answers will be in the same set. So regardless of which two numbers you take, you multiply them, they will be in this set. The result will be in this set. So for example, 5 plus 7 mod 8 in Z8, 5 plus 7 mod 8 is 4, 4 minus 5 mod 8. How much is 4 minus 5? Minus 1 you get first, but then 8 is equal to 0, so you can just add 8. Whenever you get into negative territory, you can add 8. Whenever you get into territory which is more than 8, you subtract 8. Right? So in this case it is -1, so we add 8, we get 7. 5 times 7 is 35, mod 8, we divide by 8 and we know that 32, and then subtract 32, we get 3. 3 times 7, that's interesting. How do you do 3 divided by 7? 3 divided by 7, how do you do that one? Well, first of all, you have to find the inverse of 7, right? 1 upon 7, like we talked about here. So what is the inverse of 7 in this? What is the number that I multiply to 7 so I can get 1? So we say, okay, 7, 14. So 21, 7 times 3 is 21, and we kind of keep dividing by 8. We don't get it. When we divide 21 by 8, we don't get 1. 28, 35. After that we have 42, we get a 2, plus 7, 49, we get a 1. 7 times 7 is 49, which mod 8 is 1. So what is the inverse of 7? 7 itself. Remember, since 7 times 7 is equal to 1, 1 upon 7 is equal to 7. Right? Make sense? In mod 8 arithmetic, 7 times 7 is equal to 49 equal to 1, right? Forget the 49 part. 7 times 7 equal to 1, so 1 upon 7 equal to 7. So that means the inverse of 7 is 7, you multiply it to 3, you get 21, and then you do mod 8, you get 5. What is 5 times 5? That's to be trivial. 5 times 5 is 25, mod 8 is 1. So now the inverse of 5 is also 5. By the way, you can sit down and write the inverse of all of them. It's not that the inverse of number is the same number. For example, just for the sake of it, what is the inverse of 2? You won't find it. Actually, it doesn't exist. So, I mean, that could be a problem in this case. There is no multiple of 2 which will be 1 more than 8. Multiple of 8. Right? So in this has to be organized slightly differently, right? Okay. All right. So some numbers. So in this particular case, some inverses exist, some inverses do not exist, and we will talk about that as to when they don't exist. What do we do? All right. So modular arithmetic, you can do the addition, and that is addition is commutative. So w plus x is same as x plus w. W times x is same as x times w. Associative, you can do anything first. You can do w plus x and then you do the y, or you can do w first and x plus, first you do x plus y and then do w later. Right? Or similarly for multiplication. They are distributive in the sense that the multiplication distributes over addition. So when you do w times x plus y, you could do w times x plus w times y. Remember, this is only multiplication distributes over addition, not the addition does not distribute over multiplication. There are identities. Identities means that there is an additive identity which is 0. When you add 0, the number doesn't change. When you multiply by 1, the number doesn't change. So 1 is the multiplicative identity, 0 is the additive identity. And there could be additive inverse. When there is an additive inverse, basically the sum is 0, and multiplicative inverse, the product is 1. Or actually, in both cases, the result of the operation is equal to the identity. So now, the homework, again, you don't have to submit. Now, wrong thing would be to put that thing in the Excel and hope that it will come out right, because it will all overflow and you will get the wrong answer without Excel telling you that. Maybe it will tell you that overflow, but if you just do like that, there will be a problem. So what you need to do is, you need to do in pieces. First of all, you have to know that 107 is 64 plus 32 plus something. So you start with 125 squared, then the power of 4, then you go to power of 8, then you go to power of, and every time the number should be less than 187. Right? You can go to 8, 16, 32, 64, and then you add up the appropriate powers to get 107. Multiply the numbers. And in every multiplication, you should make sure that the number is less than 187. That way, nothing overflows. Everything is integer arithmetic, and you get the answer 5. If you do a mistake, your encryption scheme will not work. We are going to use all this in the encryption later on.